I have previously put up a video on YouTube about my collection of vintage calculating devices, most of them electronic but some mechanical, and that video was limited to calculator types that I'd either owned personally and used personally or had a very close association with. I thought at this time I would make a short supplement to that video which outlines a few other interesting calculators in my collection that I wanted to share with the YouTube viewers. The first one is the Corvus model 310 or 311. Corvus was a consumer division of the famous IC manufacturer MOSTEK, and they introduced the model 310 in 1974 as a basic 4-function calculator with added square root and percent keys. The Corvus 310 makes use of the MOSTEK type MS5020A single-chip calculator circuit, which was purportedly a clone of the Texas Instruments TMS-0102 one-chip calculator circuit. According to some vintage calculator websites, the Heathkit IC 2006 model was a nearly identical calculator in a different case and missing the percent and square root keys. The Model 310 was a bare bones version of the calculator using 4 AA batteries. Corvus also marketed the same calculator as the Model 311, which was simply the same thing that came bundled with an AC adapter to plug in here. As far as I've been able to tell, the 310 also had the plug, but it did not come with the adapter. Then Corvus also sold the Model 312, which had an internal rechargeable NiCad battery pack and came with an AC charger. This particular calculator is one that's been in my family since 1974 or 1975. My parents had bought me my first electronic calculator, a Texas Instruments TI-2510 Data Math, in 1973. That calculator was featured in my earlier YouTube video. My father was an old school slide rule man and scoffed at the newfangled toy he bought me, but a year or so later he gave in and bought himself the least expensive model in the local store, this exact Corvus unit. In many ways, although the case was not so nicely styled as the TI product, and the keyboard was pretty cheap by comparison with the TI or Bowmar calculators of the day, this was a pretty nice calculator with a very clear, albeit small, display. Power switch is up on top, and the display is there. In 2016, my father was moving things around in his house and found this old Corvus 310. Remembering that I had been collecting old calculators, he gave it to me. Other than corroded battery terminals, which I cleaned up with a wire brush tool and my Dremel tool, the calculator is in good working condition. 4 functions, square root, percent, and nothing else. Basic 4-function calculator with a couple of small enhancements. The HP-35 was Hewlett-Packard's first pocket calculator. It was introduced at a time when most calculators, including many expensive desktop models, had only the 4 basic math functions. The HP-35 was the first pocket calculator in the world to have transcendental functions, meaning the trigonometric and logarithmic functions and so on, and the ability to handle exponents. And it was also the first pocket calculator to have the RPN operating system, or more specifically, the RPN method of entering data. HP had done market studies and determined that the engineering world preferred a desktop engineering calculator, and their flagship calculator product was the model HP 9100, shown here in this photo. The 9100A was the first scientific calculator, having transcendental functions such as the trig, logarithm, and exponential functions, and it was the beginning of HP's long history of using the reverse Polish notation or RPN operating system on their calculators. However, HP's boss Bill Hewlett thought that the market would support some sort of shirt pocket sized HP 9100 and challenged his engineers to develop one on an accelerated schedule. This was a risky project for HP since it involved several immature technologies that would have to happen in order for it to work. HP originally developed the HP-35 for internal use with no thought of selling it as a commercial product, but then decided to try marketing after all. At first, HP did not even have a model number for the product, and it was just called the calculator. Later on, they decided to market it with the model number 35, ostensibly because it had 35 keys. HP's marketing studies indicated that they might sell as many as 50,000 units, but within a short time they received orders far in excess of that amount, and by nearly an order of magnitude, I think they sold at least 500,000 units. By some reports, General Electric alone placed an order for more than 20,000 Model 35s right after it had been introduced, presumably for use by their engineering staff. I never actually owned or used an HP-35, although I do use the modern HP-35S every day in my engineering office. However, the HP-35 is a real classic, and I kept looking for one in good working condition that would not cost too much, and finally found this example on eBay. It only needed a replacement rechargeable battery pack, which the local Batteries Plus chain store fabricated for me for a minimal cost. I'll fire this up here very briefly. Nice clear display, although typical of the era, very small. Being RPN, you have to use the enter key. There's no equals key. So to do an addition, I simply put in, for example, 12 and enter it into the stack, and then put in a 3 and say I want to do a division, and I get my 4. This is the way RPN works. One more quick calculation here. 45, enter 5 plus. So that's the HP-35. In my earlier YouTube documentary on vintage calculating devices, I showed a small desktop calculator made by Sharp, explaining that it was just a placeholder until I could find a real vintage desktop electronic calculator. I kept scouring eBay with the goal of finding an affordable machine that did all the math logic without the use of a microprocessor or dedicated calculator IC or any other large-scale integrated circuits, and it should also use a vintage display technology. I finally found this Canon Canola Model 161S calculator pictured here, which came out in 1968. I think they only made the calculator for about 1 year. I will be showing the actual calculator in a minute, but for the moment it's more convenient to show a photo of it. All logic in this calculator is done using 123 logic ICs, just little 14-pin dips, like most people studying electronics learn to use. Almost all of those 123 ICs are early types. They're all made by Texas Instruments. They're all in the DTL or diode transistor logic family. All their part numbers start with an SN. The DTL was a type that preceded TTL logic, and even more so preceded CMOS logic that we're more familiar with today. Almost all of the ICs in this calculator are NAND gates, differing only in the number of inputs that they have. So one type of chip may have 4 NAND gates, each with 2 inputs. Another type of chip might have 3 AND gates, with at least 2 of them having more inputs than 2. Some might only have 2 NAND gates with 4 inputs each, for example, but they're all NAND gates. This makes sense because any of the other logic functions, such as AND, OR, NOR, inversions or NOTs, can be built using the NAND gates. The same cannot be said going in the opposite direction. So it made sense that they'd use NAND gates to build everything. The logic is arranged on 6 printed circuit boards that plug into a motherboard, just as on an early personal computer. The motherboard has 2 spare slots, although I don't know if Canon ever made or planned to make a version of this calculator that would use those slots. The display uses 16 Nixie tubes. The large display was necessary on here because the calculator did not have floating point math. It would always display based on the number of decimal points you selected using a large sort of rotary thumb wheel switch where you could select 0 decimal places, 2 decimal places, 4 decimal places, etc. And it would place the decimal point fixed in that position. So if you needed a fair amount of resolution and you maybe selected, 4 decimal points, that cut 4 digits off right there since it was not floating point. So and it also did not do exponential math or scientific notation, so to deal with reasonably large numbers you needed a lot of digits on the display. The keyboard itself is a very high quality type. It uses a set of reed switches that are mounted on a keyboard printed circuit board, the top of which can be seen here, with a few ICs on it that services the keyboard. And each of the keys, which sits on a sort of a frame above the keyboard circuit board, each of the switches is on a spring, but it just actuates a plunger which goes down and lowers a small permanent magnet next to each of the reed switches on the circuit board. And when the magnet comes close to a reed switch, it closes that switch. So it's a non-physical contacting type of keyboard, but with very good tactile feel, very robust mechanism, good for, hundreds of thousands of operations at least. Very fast acting, very consistent, very reliable, and nothing to wear out. I really wish they still made calculator keyboards this way, and perhaps the higher end desktop models that are still made still use something along this line. As near as I can tell from online research, this model of calculator was never sold in North America, but it was popular in Europe. It only has a 240 volt AC power capability, so I have to use a small step-down transformer that was conveniently provided by the eBay seller. This is a 4-function calculator with 1 user memory and also a constant that can be entered and then used in repetitious calculations. On initial inspection, the calculator appears to be missing the plus and minus keys. Addition is done using the black colored equals key, while subtraction is done using the red colored equals key. I don't know if this was felt by Canon to be easier for the operator to use, or if it was perhaps just done to simplify the logic design. But I haven't seen too many calculators like this. I have seen a few, and maybe for the same reasons. Other operator devices on here include the 2 memory buttons, the constant button, the multiplication and division buttons, 3 different kinds of clear, where you can clear the memory, you can clear everything, or you can just clear the most recently entered value. There's an AM key which is associated with the memory. There's a recall memory button and a reverse key. The reverse key calls back the most recently entered value, or not the most recently entered value, more like the penultimately entered value. So for example, if you were entering 1 plus 2, on a normal calculator you would enter 1 and then hit the plus key and then hit 2, but maybe before you hit the equals key you can't remember if it was a 1 you hit or an 11, and you wanted to check that. On a more complex calculation, it might not be that easy to tell by a quick review of the answer, so the RV key allows you to push that, and it calls back the previously entered value. Pushing the RV key again brings back the current value. In the example I gave, that would be the number 2. and then you go, of course, ahead and hit your equals key, and it'll show you the result of the calculation. That's kind of a cool feature. I have not seen it on any other calculator. And there's also a couple other functions here that I frankly haven't bothered to understand, like a slide switch that shows a 5 over a 4. I don't know what that means. I would have to look it up in the manual. Also, because of the large number of digits, this display has a sliding rack. It's sort of like a comb with just a few tines. You can see the points here, here, and here. And that can be grabbed by the operator and slid sideways. And it basically forms the commas that you'd have in the display, marking off every 3 digits. And depending where you've set your decimal point, or based on other user decisions, you can slide that to place those virtual commas at a number of points on the display. It's something we don't worry about anymore, but it was useful on this calculator. Here's a view of the inside of the calculator that I took earlier. That's one reason why I'm not showing the actual calculator at this point, because it's all put back together after I did some repairs, and I didn't want to take it all apart again for the video, so I'm just showing photos I took earlier. Here it shows the various circuit boards plugged into the motherboard. At the back of the chassis is this curious device. It's an interesting feature of this calculator that it does not use any memory ICs or magnetic core memory. All calculators have to have some way of storing temporary numerical values during the course of the calculation, but apparently Canon felt that available solid-state memory was too expensive, or perhaps just too unreliable at that time, so they went with an acoustic delay line device, which is this. And it was used for storage of intermediate values, and also for storage as the user memory, and also for the constants if you're in the constant mode. The acoustic delay line device was quite popular at the time the Model 161S came out. Externally, it looks a lot like a hard drive from an early 1980s personal computer. Internally, it's a long, thin, stiff wire wrapped into a loop inside the housing. I've drawn sort of a pictorial of it here with the wire straightened out. At each end of the wire is a piezoelectric transducer. On the input end of the wire, the transducer sort of pings. The electronic signal causes the transducer to change shape briefly, which is a characteristic of piezoelectric transducers. And since it's coupled to the wire, it's sort of like plucking a guitar string. And that ping propagates down the length of the wire until it comes to the other end, at which point the piezoelectric transducer there detects the ping and generates an electronic pulse. Some fairly basic logic design is used from the surrounding electronic ICs. The logic generates the original ping signal, and then the resulting red signal is conditioned by a bit of logic, cleaning up the signal essentially, making it a nice square wave, and then some recirculation logic sends it back to the input. So if you ping it, the ping takes time. Basically, the ping propagates at the speed of sound, and the wire is long enough that it takes some number of milliseconds to propagate down to the other end, and when it's red, it's conditioned, sent back through the recirculation circuit, and propagates back through the wire, and that ping just keeps going in a circle. Because the time it takes for the ping to get from here to here is fairly long compared to the operating speed of the logic can actually manage to have quite a few pings going on at any one time. So it's sort of like a series of pings propagating down the wire. And the logic can treat those pings as a series of ones and zeros. Where there's a ping, there's a logical 1. Where there's no ping, it's a logical 0. And it's all timed and conditioned so that it acts like a big shift register, and there's probably some space values or something in there that the control logic can tell the difference between one set of pings and the next set of pings, and therefore it can treat it as several binary words going around in a serial fashion. And in this manner, it can store several numeric values stored as binary serial data. There's really nothing to wear out in this type of memory, and it's actually very robust and reliable, with its major deficiencies being its large physical size, greater expense than the more modern memory types, relatively slow speed by modern standards, and inability to store more than a few numerical values at any one time. Alright, so here's the actual artifact. At this point, not a bad looking unit. I've got it plugged into my transformer, and we'll turn it on here. The Nixies power up with all 9s in most cases, although sometimes it powers up with some gibberish. And it also has the overflow indicator turned on. This is just fixed with pushing the clear key, and we get all 0s. I've turned the lamp off here to get a little better contrast on the Nixies. So when I got this calculator, the power supply was not working, the number 6 read switch had failed, and the keyboard, which had obviously been used a lot — this was a heavily used calculator, I think — it was pretty much just grungy beyond all measure, very filthy, lots of crud around all the sides and tops of the keys. There were all sorts of smudges and dried, I don't know what, on the display plexiglass and the case surface and the panel here. I wasn't able to resurrect the failed read switch. It seemed to almost be permanently welded together inside. So I looked around on the keyboard for a switch that had a working read switch that I wasn't going to use, and I thought the RV key was something that was probably the least valuable key on here for demonstration purposes, so I unsoldered the read switch from this position and put it on the number 6 position, and then put the faulty one back here just as a placeholder. So that got the number 6 key working again. I can enter 1, 2, 3, 4, 5, 6, 7, 8, 9, and actually I can keep going, fill the display up, and it just keeps going, but it will illuminate the overflow indicator. The power supply issue on here was just an intermittent connection that was easily fixed, and I had to spend a few hours with the case completely pulled apart and repairing, besides the read switch, just cleaning everything pretty thoroughly, as much as I was able to, with alcohol and various detergents. There were still some blemishes. It almost looked like somebody set a cigarette or something up here that really stained and damaged the paint in this area. But by and large it cleaned up pretty well. The calculator is in good working order except for that RV key. There's also a indicator that's currently on here. So here's the big thumb wheel switch that allows setting the fixed decimal point to 0 positions, 2 positions, 4, 6, 8, 10, and then back to 0. I've generally been leaving it in the 2 position. I'll just do a couple of math functions here. As previously described, addition is done, it's almost an RPN type of approach. So here's a sample addition problem. This indicator was lit up here before, and it took me just a moment. I had to stop the video to remember how to clear it, and it was the clear memory key that indicated that the acoustic delay line memory was full and no more data could be put into it. Therefore it could not do a calculation that required the use of the memory. So that's the kind of thing, it doesn't clear itself. You have to remember to do it when you see the indication. Anyway, so let's do a simple problem, 123, and I'm going to do an addition, so I hit the black equal key, and because I had the decimal point set to a fixed 2, the decimal point appears 2 positions in. And now I'm going to do another 123, and I'm going to push the black equals key again. Find a place where I don't get so much reflection here. And it does the function and puts the 246.00 in the display. By the same token, I can do a subtraction, and I can put in a 12, put it into memory using the black equal key, and then I want to subtract 6 from that, so I'm going to push 6 and then hit the red equal key, which gives me an answer of 6. So that's how addition and subtraction are done. Multiplication, I'm going to use 123 again because it's easy to type. I'm going to go with times, and it takes the number I entered and puts it at the fixed number of decimal positions. And now I'm going to put in a 2 and hit equal, and it gives me my 246. I can now divide that by 2 and get my 123 back. Or I can put in 963 and divide that by 3 and get 321. So all the functions are working on this calculator, except that I haven't obviously tried the memory function in particular yet. I'm going to demonstrate the constant function on here. The constant function is not momentary, it latches down when it's pushed. And now it's expecting the first thing I type to be my constant. So I'm going to put in, let's say 25. And then do my first math problem. So 25 times 4 equals 100. And now if I just put in the second part of the function over and over again, for example, I'll put in 25 and hit equal, which is the correct answer, or 2 equals, and I get the 50, 2 times 25, or 3 times 25 would be 75, and clear that out and release the constant. Here's an example of how the memory function works. AM is a latched in function, just like the constant was, and it basically means add memory, so it's going to just keep adding things to the memory whenever I type them in. So for example, 12 equal 22 equal, and the memory light is lit up saying that I'm using the memory here. 6 equal 10 equal, and now I might choose to clear, but the memory is still there. And now if I push the recall memory, it brings back the number I had. Now I can clear memory and clear the calculator. And I'll try one more thing here. Let's say that I want to add up 1, 2, 3, 4, and now that's in memory, and I can clear it, and now I can put in a 25 times recall memory equals. So that's how the memory works on here. There's one other way to use the memory on here that I didn't describe yet, and that's using the red and white memory keys. So I'm not using the add memory function, I'm not using that. I'm just going to be adding stuff to memory. So if I put in a value of 15 and hit the white memory button, my memory light lights up telling me I'm using the memory, and now that value's been added to memory. And now I want to put in a 25 and add that to memory. Now it didn't do a calculation here, I added stuff in the memory, not in the main calculator. So I can clear it out, and now if I recall the memory, I've got the result of the two things added in memory, the 25 and the 15. I can also put something into memory, for example a 30, add it to memory. Memory's in use, and now I want to subtract a dozen from that. So I can put 12 in and use the red memory key, and now call the memory back, and there we go. And while I'm going over the functions, I did look up in the manual what this switch here means, and it's a rounding function, kind of a cool function. With the switch in the left-hand position, it will round fractions up to the nearest whole number. In the middle position, it counts fractions of 5 and over as a whole number and disregards the rest of the number, and if I move it to the right, it rounds down. And finally, this key here, which is the correction key, it allows me to back up and fix a typographical error before I proceed with the calculation. So if I wanted to enter 123, but I entered 122 by mistake, fat fingered it, I can push this key and back up 1 and then enter my 3. So that's how that works.